So thank you all for coming, and all those that join online. Let me just switch things off because otherwise we're gonna keep hearing that. So welcome for joining, as I said, those coming here, but also those online, and I'll continue the presentation. Perfect. So my name is Gisela Detrell. I'm originally from Barcelona, but I've been living in Germany for many years now, and I'm currently working at the Technical University of Munich as Professor of Human Spaceflight Technologies. Before that, I studied aerospace engineering at the UBC in Barcelona, and I moved to Stuttgart for my last year, and it was so cool that I stayed there. And one more year, until the opportunity came 2.5 years ago to move to Munich. And I'm very happy since then there. Part of my team is here today as well, so you get a chance also to talk to them after. And yeah, I'm here today to talk about surviving on Mars. So looking at Mars as a whole, to get a first picture of what we are talking about, I try to look first at the positive things. So we have a longer day, so can come handy to have 20, 25 minutes extra a day. The year is double as long, so might not be that critical at your age, but at some point you might be happy to be able to say you're half your age. And most importantly, your weight is, or gravity is 1/3, so that would allow you to jump much higher. So imagine having Olympic Games in the Martian surface. So those are funny, interesting facts, but the reality is much harsher than that. We have very low temperatures. During the day, it can get up to very comfortable 20, 25 degrees, which is nice, but it goes low to -120, -130, so it gets really cold. Beyond that, we have radiation here on Earth. We're very well protected from radiation coming from space thanks to the magnetosphere. But as soon as we leave that, radiation becomes a problem for us humans. And last, the atmosphere from Mars is not made for us. It's mostly carbon dioxide, so not breathable for us humans. So all these aspects make Mars for us quite deadly. So with this scenario, with what I just presented you, how many of you would be interested in going? Okay, quite some volunteers. Some thinking about it. Okay, so yeah, it is a crazy idea to think that we can just live on Mars. But to be honest, who would have thought a couple of hundred years ago that we can fly? And I'm quite sure you've all taken a plane to go on holiday somewhere without giving it too many thoughts. Probably no one would have thought either 100 years ago that we can live in space. And probably for many of you, there has been, as long as you've lived, humans not living on Earth, but living in space, because we have had continuous humans living on the ISS for since 2000, so 26 years now, this year. In a continuous way, there has always been someone up there. So if all these things that might have seemed crazy at some point, we've managed, why not should we manage to live one day on Mars? So if living on Mars would look like this, how many people would like to go? Have I convinced a couple more? Yes. Good. So this project was, I would say, a part-time project with several colleagues from different universities, mostly Spanish and German, so it's my backgrounds together. We worked for 6 months. We met over the years and at some points had together and say, hey, we should have a project together. We are all interested in making life out of Earth possible. And it came at a time where there was a competition from the Mars Society. And the rules of the competition were to design a sustainable city on Mars for 1 million people. And the first thought from all of us was, why would I design a city on Mars for 1 million people? Why would I need so many people on Mars? But that was a given. That was not something we could decide. So our goal was to give it some thoughts, what are the challenges that we would have to face because we're not talking about one single mission with 6 astronauts, but we're really talking about something big. And that brought us together, a group of engineers, architects, scientists from all disciplines, psychologists. As you can see, architects that did very nice pictures of our design. And I would say, I don't want to say this is science fiction looking that far away in the future, but I rather see that as an exercise to be able to identify technology gaps that we might want to start working on today. So it was the first step. We, of course, worked very hard for 6 months. We did not win the competition, but didn't do that bad either. So we're in the first top 10 or top 5 from the competition. But yeah, it brought us together, and many things have come out of this project. Not looking at a city from 1 million people, but different corporations have come thanks to this project. Now, I'm talking about living in Mars, and we have seen it is not an environment made for us. It's what we could call a really extreme environment for humans. But here on Earth, we're also capable of living in extreme environments. We have the stations in the Antarctica, where during the winter, they have no way to get out. So it is really for certain months of the year, they are really isolated, and it's easier to come back from the ISS back to Earth than actually come back from the Antarctica during the winter season. We also have people living in areas with scarce resources, like think about water availability in desert regions. We can also live in some kind of a spaceship underwater, when we think about submarines that for relatively long periods of time can independently underwater. And even we can be like little astronauts underwater, scuba diving. We manage underwater also to survive for a relatively short amount of time, as long as we have gas in our bottle. So we can manage in those scenarios. Let's look then at the space scenario. So what we have here on Earth as humans, we need 3 main things to survive. We need oxygen, we need drinking water, and we need food. You have here the average values as a kilogram per person per day that we need on average. Of course, it can vary depending on the exercise you do or depending on the metabolism of each person. But we can take that as reference values. At the same time, we're producing a certain, say, waste in form of carbon dioxide that we exhale, in form of water that goes to the atmosphere or when we sweat, so through our skin. Also in form of urine and feces. At the same time, we're producing heat, and up to a certain level, we could say that for surviving, we also need a certain amount of item water. Not having a shower one day might not be a big thing, but having a certain amount of water for item purposes, long-term, it is a necessity for surviving. So we have all these things, and we can put those together. And imagine how much it would take for us to go with family or with your best 3 friends from here to Mars and coming back. So it's quite a long trip. And with that, you would be consuming quite an amount of oxygen. So 3 tons of oxygen, 3,000 kilograms. Food is a similar value, dry food. The biggest problem that we have is water. We really need to take with us a big amount of water, 13 to 37 tons of water, depending on how much water we use for item purposes. If we put that together, it's a lot of kilograms, so a lot of lunches that we would have to take to bring our things to space, and long-term making that unfeasible. But designing a space mission, it's not that different than designing your holidays. If you have a short mission, short holiday, you're going hiking for 2 days to the mountains here, you will be taking in your shoulders everything you need. You'll take your bed, your sleeping mat. You will be taking the clothes that you need. You will be taking the food. And depending where you're going, you will take also enough water for the entire trip. So everything's on your shoulders. If you're going for an exchange semester somewhere for 6 months or for a year, you will not take everything on your shoulders because that would be too much. So you pack differently. You take clothes and you assume you will reuse them. So reuse of resources is important, but you also assume that you will be able to wash them there. So you assume there will be a washing machine there will be water, and you will be able to clean your clothes to be able to reuse them. You will also not take the food for 6 months. You will take money with you, and you will buy money on the place you're going. So in space, we apply the same principles. If the mission is short, like a weekend, that would be a couple of weeks in our case, like the missions to the moon, the Apollo missions, we take everything with us that we require. we deal with all the waste that we produce, that's it. If we think about the city on Mars that I presented at the beginning, the 1 million people city, those people cannot depend on constant resupply from Earth. So they have to be able to recycle everything or get the resources from the place where they are living, so from Mars. So we talk in that case that we have some input at the beginning that we take with us, but this will be then recycled all the time. So our waste will continuously be processed so we can have new, fresh inputs. Now, today we're somewhere in the middle in space sector, what we can call a partially closed or a partially open life support system. That means that some of those outputs are processed to create new inputs, but we still have every now and then some things brought from Earth. Now, how can we do this regeneration of our resources, this recycling? Well, here on Earth, you all know from school, plants take care of our air. They take CO2 and produce oxygen, photosynthesis. They are also part of the water cycle. We also learn all at school that water cycle, you get the clouds, it rains, water goes to the river, so on. So we are aware of the cycles we have here on Earth that provide the right conditions for us to survive here. Beyond that, we can also eat the plants. So we talk about the carbon cycle referring to the food. So biological systems can do that for us. Beyond that, we also know here on Earth the so-called physicochemical systems based on physical or chemical principles. And that would be, for example, the water recycling systems we have here on Earth. For example, in many houses, there are reverse osmosis systems to purify the water. Beyond that, there are also other means of creating our resources. For example, we can produce oxygen by splitting water molecules, so we obtain hydrogen and oxygen on the process. So those are the processes that we know that can allow us to recycle our resources. Now, where are we? State-of-the-art International Space Station still for the next couple of years. And on the ISS, about 42% of the oxygen that the astronauts intake, that they use, comes from the CO2 that they exhale. So less than half, but we are already closing partially the oxygen cycle. Water, I think it's even a little bit more now. It's over 90% of the water that is used on the space station. It's dirty water that has been cleaned. So astronauts tend to say today's coffee is tomorrow's coffee, or yesterday's coffee is today's coffee, to exemplify that the water you're drinking, it will come back. So over 90% of the water is being recycled. 0% of the food is being produced on the station. I think I may have a couple of pictures later on about experiments that have taken place on the ISS, but those are small experiments. Those are not the food production systems of the station. All the food that the astronauts take as regular food, it's produced here on Earth and brought up to the station. Now, how do we do this recycling? And for that, and to have a nice break from me, I brought a video that some of you might know.
Exit urine recycler, test 1, sample 1. It's the first water we've got out of the machine. This will allow astronauts to recycle their urine and sweat into beautiful, clean, clear drinking water. First sample, transparency, subpar. Hello. Oh, that's just piss. That's just straight up piss. Smell, urine, and yeah, oh, it's piss. I don't know why I have to drink it. It's piss. It's yellow. That's piss all the way down to the bottom. Results have not been promising. Edison, you know, it took him like thousands of tries to find the right filament for a light bulb. And maybe we're being idiots, or maybe we're... What you see them drinks, and I'm going to drink it. I can say they're a fucking thing. You drink it. Do we even have a machine? Are we just pissing into this bottle? That'll go great with a cheeseburger if you like drinking piss with your cheeseburger. Hey, that's not bad.
Like a glass of water that a friend pissed a little bit into.
We made water!
Somebody give me a glass of piss, I want to celebrate.
So that's obviously a joke, but it is a reality. There's a machine on the ISS, has been there for many years now, that takes care of the urines. That's what we said, that over 90% of the water is being recovered, and that includes the urine water. So what we have on the ISS is shown here on this graphic. So we have the astronauts in the middle. It's currently a crew of 7 usually, so one more than here. And I don't think they have probably mouse on the station. But yeah, that's a habitable area of the station. Maybe I'll just use, not noisy. So we have the crew in the middle, and then the breathable atmosphere in this box. And from here, we take the air and we regulate the temperature and the humidity from this air, and we bring it to a point where we are able to remove the carbon dioxide. So you know, if you are for a long time in a room, you need to open the windows and get fresh air. And one of the reasons for that, it might be also the other, but one of the things we need, why we need to do that is to get rid of the CO2 that we exhale. If we don't do that, it would reach a level that it would be dangerous for us humans to survive. First, we would get headaches and not be able to concentrate, but it would be critical at some point. On the ISS, we cannot open the window, so it has to be actively removed from the air. And then the question is, once we have the CO2, what do we do with that? Do we process it further to recover the oxygen, which we have seen is the case on the ISS, or we just throw it away? On the case of the ISS, it's further processed, and we don't produce oxygen directly, but we produce water. So from the CO2 reduction system, we get water. This water can then be split into hydrogen and oxygen, and with that we produce fresh oxygen that can be brought to the atmosphere again. Since these people here will be using oxygen, we will need to refurbish this oxygen. Beyond that, we might need to add nitrogen, not because we're intaking it with our body, but if you have a sealed system with an atmosphere out in space where there's vacuum outside, you're most likely going to lose a little bit of air constantly. It's very small, but still that means that you will continuously lose a little bit of nitrogen that might need to be refurbished. For the water, as we have seen, a urine recycling machine exists, and that takes care of the urine and creates potable water with that. Potable water also can come from the condensate from the atmosphere. So what I said before, that from our body through the skin, we continuously bring water to our atmosphere. So that makes the entire water recovery system for what we can then get potable water. Not sure why on the ISS slides they have a shower. There's no shower on the ISS, obviously. For gravity reasons, a normal shower wouldn't work. But to represent the hydrogen water that is used. Beyond that, we have the waste going out. So there's some waste created by the humans that just is packed and thrown away. And we're missing here one extra bubble with food coming into the crew. So that's the cycle we have on the ISS. And that is based on physicochemical technologies. So still no biology in there, but only physical chemical principles used for that. If we have detail, we'll not go into the technical details, but just to give you an idea what those technologies look like or what they are based on. We have 2 systems to recycle water. For wastewater, a system with a chain of filters that are each capable of catching different type of particles. And for the urine, we need a distillation process. Distillation process is something we have here on Earth for many other applications as well. And that can be used also to recover water from urine, which contains a lot of toxic elements for us humans. So we cannot that easily filtrate the urine, but it needs to be through a distillation process. And just to give you an idea, those 2 big boxes here, these are 2 standard racks from the ISS, so a little bit like a wardrobe size. And there are 2 of those that take care of the recycling of the water of the ISS. Beyond that, we have the technologies in charge of the air, so of extracting the carbon dioxide, processing it, and then providing oxygen. For the oxygen, I've already mentioned, that's water electrolysis, so splitting water into hydrogen and oxygen particles. And for that, we have the electron, the Russian system, and the oxygen generation system, the American one. The picture is from the Russian systems. And from the CO2 removal, again, we have 2 technologies, the American Vostok and the carbon dioxide removal assembly from the American side. They are absorbent beds that are capable of trapping CO2 particles when the air goes through. So certain materials where the CO2 particles get trapped. And then there's also the Sabatier reactor, which is the technology that takes care of processing the carbon dioxide, reacting with the hydrogen, it creates methane and water. That had been in the station for a long time. It was brought back for refurbishment. I'm not sure if it's up on the station at the moment or not. Now, I've mentioned here Russian and American technologies. Do we Europeans also have technologies on the life support system area? My students say yes, good, you learn well. Yes, so yes and no. There has been a technology demonstrator for life support systems. It was built by Airbus in Bodensee under the contract from ESA. That was called the life support rack or advanced closed loop system. It was up in the station, or it might still be up on the station, but not operational anymore right now, since 2018, I think. And it's also one of these wardrobes. So the water was 2, this is 1. And it contains the technology to supply the air for 3 people. So we have the 3 astronauts here. We have the system that takes the CO2 using a certain material, in this case, amine, to absorb the CO2. A Sabatier reactor I just mentioned that produces methane and water, and then water electrolysis to produce enough oxygen for the crew. That was not a part of the life support system of the station, but a technology demonstrator. It never fully worked as a cycle. They tested the different compartments or the different technologies, the 3 blocks separately. They had several problems, especially with the Sabatier reactor that they tried to solve. But I don't think it ever fully worked as a cycle. But a lot of lessons learned have been put together on that to look at the further development of life support systems from Europe side. So it is, a technology demonstrator that has helped us a lot to understand how certain things work and how other things don't work. Beyond that, there's the food, as I've mentioned before, all produced here on Earth and brought to the station. It can look like the pictures you see here, so in some kind of bags, vacuum bags, that can where the food has been dehydrated. So the first step is to put water back on the system, but also cans like you have at home. So the food that is sent to the station, it needs to be able to stay there for long duration, for a long time. You cannot have things that within a week they are bad. So at the end, it's quite similar to food you might have at home with your cereals. There's usually also dehydrated fruit and things like that. What makes the food special is the long shelf life, and also in the case of the American astronauts, I guess the Russian is very similar system. They have quite a big menu of things that they have, and they choose for their flight what they want to take and what not. For the European ones, since we have less, we have been more picky, and for each astronaut, there has been some specific meals that have been extra produced for those astronauts. So when German astronaut was in the station, there was German typical food brought with him. When Italian astronaut was up there, special food was prepared for her. So since we have less, we can be more picky on that and make food for every special occasion. And it has been usually also an event around it for that special food produced for that specific astronaut in every country then. So what's last? We have the waste. As I've said before, we pack things properly, and what happens after that is it gets burned during re-entry in the atmosphere, so we dispose the rest of the waste that we produce beyond what we have seen with water and the air. The solid waste gets burned through re-entry. Now, that's where we are today, state-of-the-art technology, what we have on the ISS. And the goal long-term is to go towards that city on Mars, where we want to have 1 million people living independently from Earth. What we can do to get there? Well, we have to recycle as much as possible, because we cannot depend on bringing resources from Earth. So from all the waste we are producing, and that's not what we're doing today yet, we need to be able to recover fully, or we use the resources of the planet. That's, of course, also an option to complement that. So to do that, we can improve our physicochemical technologies. Right now, we're able to recycle 90% of water. We can improve that and get higher. From the oxygen, we are recovering half of it, more or less. We could improve that and get more. If we do that, we might be able to close the oxygen and the water cycle, but we still have the food problem. To solve the food problem, we need biology. Without biology, nowadays, we're not able to produce food. We can think about 3D printing food or things like that, but the material that needs to be used has to come from somewhere. So at the moment, I would say we don't come around without biology. Now, what has been done so far on that direction, biology for space? The first example I like to show, it's from the 80s, late 80s, was constructed. Has someone heard about Biosphere 2? Yeah, what can you tell me about it?
Well, it was this experiment making this ecosystem that was like closed, but
Yeah, so closed ecosystem, maybe some other keywords.
I think the problems with the steel, like the Stahlbeton. That's
Yeah, the problems with the materials, yeah.
I think it did not sustain for a long time.
It did not sustain for a long time, yeah. Those are all right ideas. So I especially like to explain this because it's a long time ago, so it shows we've been working on those things for a long time as humans. It was a closed environment in a building. So you see this building, which is quite huge. There's no one, or there's a small car here, or some trees here. So you get an idea of the size of the building. It's 16,000 square meters, and it was gas tight. So it had its own atmosphere, completely separate from the outside. The only thing we could argue is, okay, those are all windows that they were getting sun energy, so they were not fully isolated in that sense. But beyond that, they had their own earth inside this building. And that's actually why it's called Biosphere 2. Biosphere 1 is our earth. It's not that there was an experiment before that. In this huge building, there was the first experiment lasted for 2 years with a crew of 8. And they had several problems. The list is long. So they had in there different types of plants, different types of environments from different areas of the world. They had animals, they have insects. So it was really a small earth built in there. They have problems of insects overpopulating, insects getting completely exterminated, dying out in the system. They had plants not growing as expected. One of the things you never think as an engineer is if there's no wind inside, the plants will not grow the same way they grow out because the wind makes the plants stronger. So things like that were observed on such an experiment. During those 2 years, they were not able to sustain the right conditions that we need for humans to survive. The oxygen decreased. And the oxygen decreased because the material what the building was made of was capturing CO2. And because the CO2 was being captured, it was not being recycled in the system by the plant, so not enough oxygen was being produced. That implies that the oxygen level would start going down. It went down to a level that they thought it was starting to be critical. So they tricked the system. I don't know exactly when within those 2 years, but they put some extra air in there. So it was not fully closed for 2 years. The list of problems continues and is very long. There's a nice documentary and a couple of nice books about it if you're interested in knowing more. There was a second experiment after only lasting for 6 months that ended more for, I would say, political reasons than scientific reasons. There were some disagreements and they opened the door at some point from the experiment. So it was not a closed experiment anymore. So that was ended before plan. For me, the big lesson learned without looking into the details is that reproducing our Earth in a small environment, in a small volume, it's very hard. Here on Earth, we have a huge atmosphere. Compared to this building, our atmosphere is huge. We have the oceans. So we have a lot of buffers in our system. We know that things on Earth are changing and we have increasing CO2 levels, but it's not a problem within a couple of minutes. It's a long-term problem, but not within minutes. In such a system, without all these buffers, a problem like that can have very bad consequences within weeks. Without having these buffers, things can go wrong very quickly. So does that mean we should not rely on biology if we want to go to Mars? Maybe not in the way of let's have an Earth in a building and let's hope that everything stays on balance. That doesn't discard biology, but makes us think, let's be cautious on how we use biology. That brings me to another experiment that has been running already for, I think, over 30 years in Europe, which is called MELISA. MELISA is a partnership of several research institutions overall Europe, and they are all specialized in different areas of biology. And their goal is to put together a system using biology in a more simpler way to recycle all the things that we humans produce and get all the fresh resources. I'll not go into the details, and I'm not a biologist, I'm an engineer, so I cannot go into more details than what I'm going to explain. But the main idea is we have the crew producing certain waste in a solid form, but also the CO2, as you can see here. And we have 3 different compartments with 3 different types of bacteria. In each compartment, there's only one type of bacteria, one living organism, and several cells of that, but only one type. And each of them has been very good studied, and we know how this bacteria reacts to changes on light, changes on temperature, changes on the inputs that we provide. So we know how to control this biology. So the idea is that the first compartment is able to break the waste that the human produces in other substances. Again, without going into the details, those substances are the input required by the next bacteria, and so on until the next compartment. And the last one is able to provide the nutrients, the minerals and nutrients that higher plants would require to grow. Those higher plants are then linked to the humans. The humans can eat those, and at the same time, water is being recycled on the process, and the oxygen is being produced through photosynthesis using the CO2 that the astronauts exhale. So we use biology, but in a more controlled way. This is an ongoing experiment for many years. There's a pilot plant in Barcelona where they are putting all these compartments together. I think they have managed to get them 3 working, one after the other, but not yet fully close the cycle. But they are planning soon to have crew included in the loop. They've been doing tests with mouse at the moment, not with crew, but that is coming in the next year. So it's a long-term ongoing project. Still not designed for space. The different reactors that are used to grow these bacteria, for example, they are gravity dependent, so it's not a system that we could send tomorrow to space, but they are in parallel also working on the space adaptation of these different compartments. I'd like to mention a couple of other more projects. There are more. This is really a selection of the projects I like the most, I would say. So it's a biased selection of projects. But ENISS is a project with different countries involved that was led by DLR, German Space Agency. And it's basically 2 containers, also gas-tight or as gas-tight as possible, that were brought to the Antarctica. Those containers are basically greenhouses with very efficient growing systems to grow plants. Now, it's not the same to go to the Antarctica that to go to space. And of course, they had to start with Earth's gravity here. But they had to grow plants with aquaponics in an isolated environment where humans were not interacting with the plants all the time. They have limited access to these 2 modules. They were, I don't remember the distance, how far away they were from the station where the humans are, but where they live. But they had to gear up to go out to the cold temperatures and the snow outside. So a little bit like doing an EVA in space, more or less, to get access to this facility. So there was a couple of people staying for an entire year, so each one staying for a year in the Antarctica and running this experiment. One of the interesting thing here is one of the goals was, of course, to develop technologies to autonomously grow plants. But it was also interesting to see how the crew from the Antarctica that have nothing to do with space, they were very happy every now and then to get their fresh food. So the psychological effect when you're in isolation of getting your own fresh food produced has a very high positive impact, or mostly positive impact, on the crew, which is something we might also consider for space applications. So even if Antarctica is not space, there are several correlations on things we can learn from. So all of the experiments that I've mentioned have been happening here on Earth, but there's been also experiments in space, and it's a collection of pictures of different platforms that allowed for experiments in space. That's veggie. That was the first salad that was I think then eaten by the crew. It's not the enough salad was produced to sustain the crew, but at least they had some fresh salad. This is a very simple system, quite open to the atmosphere of the ISS, but that allows for very quick experiments to see how different lighting affects to the plants. You can see here, it all looks rather lila color. It's red and blue lighting that it's used to grow the plants on this picture. So you can test very quickly different parameters and how that affects the plant. Then there's a more advanced system with a closed environment. So this is a closed system, a closed box with its own atmosphere. So we can also check effects on different CO2 levels, different temperature, humidity, and so on. This is relatively small. It's like, I don't know, microwave size, more or less. Similar is the Russian system, LADA system, which you can see here in the picture. I'm not sure how the Russian research is going. As far as I know, the Americans, unfortunately, are not using those at the moment because of the cuts they had in their budget. But they have been there for many years now. I bet it's over 10 years at least. So yeah, there's been several experiments on those platforms. The one on the right is a platform that has long not been on the ISS anymore. It was an European technology. And what I like to, I put that to emphasize one thing. So you see two doors here. There are two different compartments inside. And they are actually circular compartments that can rotate. When you rotate, you generate artificial gravity. So you can imagine here having one system still and the other one moving at the right speed to generate 1G. That allows us to run an experiment at the same time with the very same conditions, same atmosphere, everything's the same, with one system in microgravity and the other one in 1G. That was interesting to have this comparison from the experiment. You don't run one in Earth and one in space, but you actually have both up there. The was an European technology and was unfortunately, it was decided to stop using it and was brought back to Earth. But it's also technology that would allow us to simulate Moon and Mars gravity. So we could see the effect of a different level of gravity on plants. Plants feel gravity and they grow accordingly. The roots go to the bottom. And once we don't have gravity, the plants grow differently. And we don't know how much gravity is enough gravity for the plant to feel. So it could be interesting to have systems like this that can rotate to actually simulate different levels of gravity. Now, those are all, to say, higher plants that have been studied. What we do in our group in Munich and what I've been doing the last years in Stuttgart before that, it's not related to higher plants, as you can see here, but an alternative that we consider to the use of higher plants, and that's microalgae. I forgot to bring microalgae with me for you to test today, but I would say you can be happy that I don't have them. They are very salty. I always like to see the faces of the people trying that when during my talk. They are really salty. I don't know who has tried our algae. I think the students on the back may have. Good or not? Yeah. Okay. So algae might not be that tasty, but they are very rich in protein. So it's actually something that is widely used here on Earth as a food supplement. You can find them in supermarkets, in several products. There's a little bit of algae. Keywords here are either spirulina or chlorella, or the two in the market. Wiley's salt. And we talk about microalgae, so very, very, very tiny algae. The picture is taken with a microscope, so what you see here are the algae cells, and usually you would only see a green liquid where the algae are living. And I love working in this field because it's as interdisciplinary as it can get. We need to understand, obviously, the biology. We're talking about living organisms, and they have their needs. We need a life support system for them. They need a certain temperature. They need certain nutrients. But at the same time, if we want to use that for space applications, we need to focus on the technology as well, because we need to make sure that those algae have this right environment for 10 years. We're not talking about a small experiment on our lab that might last for a month. We're talking about the system to cultivate algae in a continuous, robust way for 10 years. And that's a big challenge. That's not something we do here on Earth. On Earth, algae are usually cultivated for much, much shorter periods of time. Now, I did a lot of research with my colleagues in Stuttgart the last years. We had several experiments on the lab, and we got to the point that we got the funding from the German Space Agency to send our experiment to space. So we designed a system that works in microgravity. And microgravity comes with many challenges that are not only for the algae part, being the biggest one, that we have a system that has water, the algae live in water, and they produce oxygen. So we have to deal with the water and gas phase. And separating those on gravity environment, it's very easy. Water will stay down, bubbles will go up, the oxygen that our algae produce will come in forms of bubbles and will raise. once you have microgravity, bubbles don't go up. So you have to figure out how to separate the gas and the liquid. And that's not a problem only for the algae. There are several fields of study work looking on that for microgravity applications. So we designed our experiment, and we wanted to be able to test that for 6 months. We wanted to show this is not something that works only for a couple of days, which is the case usually with biological experiments. We want to show that it can work for 6 months. We sent our experiment up on the station. That's the chamber, how it looked like, where the algae grows, and that's on Earth, a sample of the algae very concentrated after 6 months. And the picture on the right is a picture taken on the ISS, so we can recognize the background of the ISS. And that is a sample of algae after growing 2 weeks in space. So we had our experiment box, and we had astronauts inserting the algae at the beginning, and after 2 weeks, they took the first sample, and that should have happened every 2 weeks. I think 2 hours after this picture was taken, I was on holidays back home with my family in Spain, and I got a call, your experiment is off. Like, what do you mean off? Okay, it's not working. Okay, what do you say? Have you tried restarting it? They tried everything they could. If in your house your TV suddenly turns off, you'd probably check if it's a TV only, if it's entire house, entire neighborhood. Should I change the cable? We tried those things in space. At your house, it probably takes you 10 minutes to check where the TV problem is. In space, it took us, I think, more than a month to check all the options, because you have to plan astronaut time. If you need to change a cable, they first figure out which cables we have on storage and which one will be suitable for that. And then they plan that a week after, the astronaut takes that cable and changes it. So you can see that things take much longer. So imagine as a scientist that has worked for years on the algae experiments, and then finally we'll get our experiment up there, and after a week, 2 weeks, something like that happened, and you have to wait for a month to even figure out where the problem is. The bad news is we never figured out where the problem was. They didn't manage to restart our experiment. It never was brought back to Earth. It was one of those things that got trashed and burned during re-entry. So we'll never figure out what happened. It was hard. It was a really hard moment. But we learned from everything. And for me, it was interesting to see with engineers, or me as an engineer, I tend to worry about biology. Like, it's complex, it's not always the same. I'd rather have my mechanical things that I know how they work and that I can study better. But the thing is, if a mechanical thing fails, it fails. You either repair it, we might get to a point where it's self-repairable, but nowadays you have to repair things yourself. With biology, if we would have managed to get the power on again after 2 weeks, the algae would probably not have been in their best state. With lack of light and movement, several cells will have probably died, but they would have recovered. So it's a system that it has a capability of self-recovery. So for me, that was a good example. Okay, as an engineer, I should not be that afraid of biology, actually. That might be a good solution for space, because we need something running for the long term. So we might want to have something that is able to recover on its own. So we're continuing now the work. So that is from my Stuttgart time. Now we're continuing the work with Stuttgart. And as I said, there are a couple of colleagues from the group here today. And we have a huge lab, the Algae Tech, that we're doing our research in. And we hope to look at lunar-based photobioreactors in the next years, on how to design a reactor for a lunar base, maybe build a system that is big enough, because for a person who would probably need a couple of hundreds of liters of that photobioreactor. And that's something you usually don't do in closed environment. So that's something we would like to try in this big facility that we have now. And with that, we have not solved the city on Mars with that, but we're looking at one of the aspects that will be highly relevant, which is the production of food in situ in a very efficient way. And with that, I'd like to finish my talk with the last slide saying, I don't think that would be the case today, but with the general public or with families and children, when I give a talk like this, the first question that comes is, why do you think about designing a city on Mars for 1 million people? Don't we have enough problems here on Earth to solve? And the answer is yes, absolutely. We have enough problems on Earth here to solve. And I'm not thinking about a city on Mars of 1 million people just for the sake of going to Mars one day. We are thinking on which technologies we need to design to live in a very harsh environment. We're talking about an atmosphere that is full of CO2. We are talking about we humans produce CO2 and we have to take it out from our atmosphere and do something with it. We're talking about using water in a very scare way, that we are as clever as possible with our water usage because it might be a limited resource in space. So all these things that apply of living in an extreme environment might be useful today here on Earth. We have problems of our atmosphere with increasing CO2 levels. We see more often that we get periods where water is scarce in certain regions. It was in Spain a couple of years ago during the summer, a big thing that we needed to figure out how to live with less water a day. So when we think about Mars, yes, I hope that one day we'll have a city like that on Mars. In many, many years, I will not see that myself, but that we work towards that direction, but never forgetting or always keeping in mind the Earth and how this technology can help us on Earth as well. And I think with the life support system, there's a very direct link because we are the ones using these resources and we need them as well here on Earth. So with that, I come to the end. I really hope that will happen one day. I hope we'll see the first people on Mars, at least in my lifetime, not that far as shown in this picture. But yeah, my goal and from my team is to work towards bringing a big piece, a small piece of what one day would be needed inside the city by producing oxygen and food by using biology. If you have any questions, I'm here for now. You also have my contact data. And again, there's more people from the group, so there's room for discussion here with more people if you're interested in. And yeah, thank you all for joining today and also those online. It's been a pleasure being here today with you all. And I hope you have some interesting questions. Yeah.
Thank you very much. I'm just curious in terms of like resources on Mars. So, I mean, what are, I'm not extremely aware like now the current status of, all this about having water on Mars. So what are like the really very useful resources there that, would be very, would lead that you would need to take less stuff from here there?
So the most important thing for us is water, not just for the humans, but also for propulsion purposes. And there has been, I think, enough evidence that is very likely water on Mars. But that goes beyond that. So one of the things we did in this project, and again, that's long-term planning, we really look, if you want to, one thing is if you send 6 astronauts, you probably bring most of the things with you for the first 6 astronauts we send there. And then as you keep increasing, you might start using resources. So it's not like tomorrow we'll start using resources from Mars fully. But long term, if you want to build a city like this, it has to be built with materials from Mars. So one thing that we did in the study, and it's not my field of expertise, but I can check the data, is we look at what materials do we use here on Earth. When we construct a city, what do we use? And what things make sense also to use in space? So we looked at that. And then which materials are available on Mars? Some things we might be able to find there. Others we might be able to transform. Others we might need to find a substitute material. So it goes to all directions. But the key element for shorter term, it's water. It's clearly water. But we can start thinking about if we can get minerals for the plants and things like that with construction material. You want to produce solar cells in situ or solar collectors. You would start looking at the different materials available, minerals available, and what you can do with that.
Thank you for the talk. I was wondering, because at the end you said that by addressing the Mars mission, we can also address problems on Earth. And I was wondering if we could, with the same thing, we could also, does it address the question of discovering other forms of life? So like by trying to figure out ways to generate life, does that also kind of play into the research of, the big question?
That's a very good question. I'm an aerospace engineer, so I don't feel I can reply to that at all. Yeah, that we know life as we know. If there's other ways of what we call life, that goes beyond all my absolute knowledges. But again, from doing research for space, we learn from everything. So it definitely brings us more knowledge in all directions. So it can solve problems that we have on Earth, but it can also help us come up with ideas that we probably wouldn't have, because you design systems that are for a very different environment. So you really have to change the mindset. So I would say in general, yes, that could help, but I cannot go into the details specifically. But very interesting point. If you have biology questions, our biotechnologist is in the room. Address them to Sergio. Otherwise, Lina and Timon are working on the design of photobioreactors. So if you're interested in more, I'm sure they will also happy to talk to you.
Yes, do you think Mars is the best candidate planet or to establish a human presence, or have you considered Venus, the moon, or some moon of orbiting around the solar system?
We are from, so this project was particularly Mars. For all our research currently, we're focusing on the moon and Mars as the more likely scenarios to happen on the coming years, because even if Mars is not made for us, Venus is even worse with the atmosphere. So it goes to other levels of complexity compared to Mars. And the moon and Mars are the closest thing we have. So it still takes a very long time to go to Mars, but it's still, I would say, reasonable. But going farther than that with the propulsion systems that we have today, I would say for human missions, unthinkable. That might change, but right now, no. So we are for the, I don't want to say short term because it's not short term, but mid-term, we concentrate on Moon and Mars. Okay. Yeah.
So from experience, so how is the current status of Europe compared to the US? Concerning budgets and so is this? I mean, because I know in the US there's also now currently some kind of commercial interest. So which is going just beyond just scientific research. So is there any signs of something like this in Europe or?
Yes, we are behind the US in many sense on that aspect, or Russia for that sense on they clearly done more human spaceflight than we have and have more experience on that. But we're also working on that, and there are examples like we have the technology demonstrator, life support system, but there are also an increasing number of companies now looking at human spaceflight factor things, or even looking at experiments. In Germany, there's URI that do small biological experiments that can also link to biology used for life support systems. From a bigger scale, Airbus is part of Starlab, which is looking at one of the private stations, not only Europe, it's mostly American, but with almost half of it being European as well. So we're doing steps on that direction. But of course, we are behind in, I cannot put a number, but we're clearly behind number of astronauts, number of missions. We don't have our launching system that can bring astronauts up. So we're clearly behind, but still there are a lot of initiatives happening, and also in the private sector, it's happening in everywhere in the world. So we're getting there slowly.
I have a question online.
Mm-hmm.
What kind of infrastructure would we need to go to Mars if the goal is 1 million people on Mars? For example, a space elevator or a moon base would be an efficient first step?
Those are good questions. Yeah, those are possibilities. For me, this scenario of 1 million people on Mars, or even 10,000, still sounds too crazy and too far away in the future. So I've never properly thought of all the steps, but the scenarios that we envision in a longer run, it might include the moon or the moon surroundings as a staging base. There are many studies looking now at the in situ resource utilization from lunar resources. So maybe that we can produce fuel on the moon. So we don't leave from Earth, but we go to the moon vicinity. And then from there we go farther away. So the moon as a as a stopover on our way farther away definitely is a thing. Space elevator, it's also been a topic in discussion for many, many years. I think it comes with high technical challenges at the moment, but we're talking about the faraway future. So I would say let's get crazy and keep our minds open and not discard things yet. But yeah, there are many things out there that might change the game at some point, but they are still at this moment not very realistic. And I would say the space elevator might be one of those critical things that who knows if we will be able to do that.
Thank you.
Is there for your team or another lab in Europe some plans for new experiments in the ISS to test those closed loop cycles?
From Europe, I know that there's a group in Belgium working also with algae. We work with chlorella, they work with spirulina, so we're each looking at the different species, but the two most likely. And they have sent a couple of experiments already, and they might still have one on the ISS. We don't have the ISS for that longer anymore, unfortunately, so we'll have to start looking at the private stations, I guess. So from Europe, there's definitely another group working with algae that have had also a couple of experiments with different goals. They are more the biologists looking at the biology, and we have been thinking bigger on the technology side. I know that things in the US have been harsh this last year. Those experiments with plants are not taking place at the moment because of all the cuts they had, unfortunately, on the science part of the budget. So there are things happening. Maybe it has slowed down a little bit, unfortunately, now, but there's definitely, and I think I don't have the information because it's not that easy to find, but I'm quite sure in the Chinese space station they are doing experiments with plants and probably with algae too. So I'm sure there's research also in there, but it's not that easily accessible to find. But definitely they have a similar station with similar capabilities to the ISS, so I would assume yes. And there were plants on the moon already. The Chinese had an experiment on the first side of the moon, so yeah.
Is the algae being researched only for food, or are there other use cases for it in space or Mars?
So the algae have the nice thing they do photosynthesis, oxygen production. We can eat them, and they also help us recycling water because they take some of the substances out of the water. So we can think about the biomass produce the oxygen on the water recycling. Depending what you want to do, you can have them all, or you'll have to take two of those. If you want to produce food for humans, it might not be wise to use the algae to recycle water, because then within the algae, you might have things that are bad for us. But the biomass doesn't necessarily have to be food for humans. It can also be used to produce bioplastics, or it can be used to feed fish in a long-term plan, but it can be the food for something else that we eat then. So there are several options, and we can play with all these factors. Do we want to produce clean water? Do we want to produce oxygen? Are we interested in the biomass? So those are the three main outputs that you can get, and you play which one you get and with which quality you get it.
For the development of such high support systems, how much does it help to have the gravity of the Mars or the Moon when compared to zero-G?
I would say it helps a lot just by the fact that what I explained before, separating gas and liquid in microgravity, it's a nightmare by itself, and it comes with several problems. So technically, the systems will be easier. The algae themselves, when we're talking about this microalgae, they are unicellular organisms. They don't care. They are floating in a liquid. So for the biology side, most likely it has non-effect on the algae cells themselves. It could still have some internal process, but most likely not. But it's more about the technology, the system that we have. So having some gravity makes the gas-liquid separation easier. At the same time, however, when you have gravity, if the cells are heavier or more dense than water, they tend to go to the bottom and sediment. And in microgravity, you don't have that. The algae are all floating equally within the liquid. So it also comes with some advantages, but I would say technically, it is a challenge to separate the gas and the liquid. It's feasible, it can be done, but it is an extra challenge that you don't have when you have gravity. And less gravity, it's still good enough to separate the gas.
I have to, oh, sorry. Please go.
So right now we're having labs that are starting to produce lab meat and lab cheese and milk. So how useful would these kind of products be for space missions? Could they be used? I mean, where's the difference in how the products are created in labs here on Earth, and they would probably be created explained?
That is a very good point, and I don't think short term it's still going to be very relevant. But for a city like that, that's what we plan. One of the food sources you'll have will not have cows that produce meat, but we can produce meat by other means. So that's definitely something I think that will play a role. This is not my field of expertise at all, but from what I have read, I've seen so far, it's something feasible, but still very expensive in terms of resources required to do that. So it's not worthy, let's say. But who knows? It's a long-term plan to have so many people on Mars. So maybe we're at that stage that that's feasible. So I think it will play an important role, yeah.
And I have two last questions online. So the first is, any idea about giving a magnetic field to protect Mars that would help in improving the atmosphere and ability to grow food?
So I've always I've heard about the idea of creating a magnetic field on Mars rather to protect us from space radiation. That would be huge. I think that's technically infeasible, not feasible at the moment. So it is a nice concept to say, well, also for the humans to create such a field that would protect us from the exterior. Again, not my field of expertise, but from everything I've read, that is unfortunately technically unfeasible because we're talking about the huge magnetic field that would be required.
And the last one, do you think it would be practical to build infrastructure on the moon first and then use it as a starting point for missions to Mars? Would that actually save fuel and costs in the long run, or would it just make the mission more complicated?
So having the moon as a first step, it makes sense for many reasons. The first one, because the risk is lower, because going to the moon and coming back takes less time. So having a first habitat permanently on the moon, it's something we can use to learn and to try technologies. So it's definitely it might be an important starting point, because going to Mars takes several months. So yeah, the risk of something happening and then being able to bring the astronauts back relatively quickly or not changes a lot. So definitely, but we also have to keep in mind that the atmosphere, the conditions from the moon and Mars are very different. So there might be technologies that we would like to have on Mars, like creating oxygen from the carbon dioxide of the Martian atmosphere, that we cannot use on moon. That the moon doesn't have this atmosphere, so it doesn't make sense. So there are some things that are different, but from just from the risk point of view, it makes absolute sense to let's first try things on the moon. If we're able to live on the moon for continuous time, let's make the next step. That would be a stepwise process, so to say. Okay, then I would say thank you all for having me.